Nowadays, a nuclear power plant is an important element of emission-free energy. In this video, we will show how such a power plant actually works, what it consists of, and why the reactor is called the heart of the power plant. After understanding the principles of heat generation by the fission of atomic nuclei, you may be surprised to learn that apart from the primary circuit with a nuclear reactor and a steam generator, it is essentially a normal thermal power plant with a turbogenerator, a condenser, and a cooling circuit. A nuclear power plant is an energy facility used to produce electricity. Although it is called nuclear, it actually consists of both nuclear and non-nuclear parts. The nuclear part of the power plant is enclosed in a hermetic concrete cover called containment, which protects the facility from external influences and, conversely, prevents radioactivity from escaping into the environment in case of an unforeseen event. The entire primary circuit, consisting of a nuclear reactor, a steam generator, and a system of connecting pipes, is located in the containment, and a slight underpressure is maintained in it during operation for safety reasons. The primary circuit is immediately followed by the secondary circuit, which is located in a non-nuclear part of the power plant in the turbine hall, right next to the containment. The place of contact between the two circuits is the steam generator, where the heat is transferred from the medium to the primary circuit to the water of the secondary circuit, which then produces steam that drives the turbine. The most important device of the primary nuclear part is the reactor. In the reactors that are used the most, it consists of a steel container capable of withstanding high temperatures and pressures. The pressure vessel is connected to other parts of the primary circuit by a pipe. In this heart of the power plant, rods with nuclear fuel, made mostly of enriched uranium, are stacked in the core. The controlled chain fission of fuel nuclei, taking place in the reactor with the help of neutrons, is the source of a large amount of heat. The released heat is removed from the fuel rods in the reactor by a circulating cooling liquid, most often water. In this case, the water serves not only as a cooling medium, but also serves as a moderator or decelerator of neutrons, which are used to split uranium nuclei. It was discovered that uranium nuclei split more willingly when they are hit by neutrons with low energy. Every time the atomic nucleus of the fuel is split, a certain amount of energy is scattered into space and neutrons are released, and they are capable of splitting other fuel nuclei after slowing down. The amount of fission reactions and thus the power of the reactor can be regulated by the operator by inserting and pulling out control rods with neutron absorbers into the core area. This disturbs the overall neutron balance in the reactor. When the rods are inserted, there is an increasing shortage of fission neutrons. The number of fissions of other nuclei decreases. The power decreases until the fission reaction stops completely. When the rods are pulled out of the core, the situation is the opposite, and the power of the reactor gradually increases with the increasing number of neutrons that are no longer absorbed. The heat output of the reactor is transferred to the steam generator by means of hot water. There, the hot water flows through a system of heat exchange tubes and transfers heat through their walls to the water of the secondary circuit. The secondary water, with a lower pressure than the water in the primary circuit, begins to boil, and steam is produced. The strict separation of the two circuits ensures that the radioactive water of the primary circuit does not come into direct contact with the turbine or any other non-nuclear part of the power plant. The dense steam produced in the steam generator flows through the steam pipes to the turbine. Its kinetic energy exerts force on the blades of the impellers and spins the turbine rotor up to a respectable 3,000 revolutions per minute. When the steam expands in the individual stages of the turbine, its pressure decreases and its specific volume increases. Therefore, the blades at the last stage must be significantly larger and longer. The turbine rotor is directly connected to an electrical generator, in which mechanical energy is transformed into electrical energy. The constant speed of rotation of the rotor ensures a stable frequency of the produced alternating current. After the necessary adjustments to the voltage levels in the output transformer, the produced electricity can travel to the distribution network. In order to fully utilize the energy potential of the steam in the turbine, the steam must condense as it exits the last stage of the turbine. Condensation takes place on cold condenser tubes under pressure. The cooling of these pipes is ensured by the water of the separate tertiary circuit of the nuclear power plant. The water can be cooled either directly by sea or river water, or by natural or forced draft cooling towers. The working principle of a nuclear power plant is very similar to other thermal power plants in the secondary part. The main difference is in the heat source, which in nuclear power plants is the process of fission of nuclei of heavy elements in fuel taking place in the core of the nuclear reactor. Due to the potential danger of emerging ionizing radiation, the technology of the primary circuit must be well secured and the power plant operated in a high-quality manner. The reward for more complex construction and ensuring safety is a prospective emission-free and reliable source of electrical energy.